that is geography. But when you started drilling the inside of the body, intestine, kidney, liver, that becomes geology. So same thing we do in the geology. We study both exterior and interior. Next, have watch this small video.
Geology is the study of planet Earth. It's a really outdoor-based subject. The real world is our laboratory. We get students to work together all the time. So it's very much community-led learning rather than individual, which we think works really well for students in the real world, particularly as part of a team that they would do in their job in the workplace. Without geology, we would not be able to use our resources of our planet. It's the foundation for everything that we do. So all those resources, all those minerals, all those materials that we use in everyday life are a result of geology.
So here we come, what we study, the subject matter of geology. The first thing is this external surface study, physiography. Then what are the materials? Minerals, rocks, structures, everything that you see on the rock. Then that is the interesting part, phenomenal process. Now everyone knows that we are lying over some plates, and those plates are continuously moving even today. So that study of plate tectonics came after 1960. So in few further sections we will deal with it more. And the other thing is life. So we study of the present and past life, and even in some part of geology we study or evolution of man, evolution of horse, evolution of fishes, evolution of elephants, everything, and how the changes have taken place. Now, the first unit that is taught in geology is physical geology. It's just a physical aspect of geology, that whatever you see externally and how they are formed, like mountains, rivers, glaciers, earth, volcanoes, streams, and any structure, desert, sand, dunes, anything. So they have a typical process of formation. And because if I try to explain those things, the lecture will go maybe many hours. So just let us focus on the brief. Now here you can see, I'm trying to explain. Now you see, these are aeolian deposit, means these are made by the action of wind. Now you can see here dunes. So this structure, they are having a definite pattern. So here you can see the wind direction. Wind is coming from here and they are depositing here. Now this is a glacial landform. And this is called karst topography. Karst topography means underground. Here we get leaching and solution. And maybe in the tourism sector, there are a lot of underground caves that people visit. And this is a alluvial land flood. This floodplain means channels, floodplain. This is made by a river. If you see a big river plain from the space, you will find it like this. And this is interesting, V-shaped valley. Actually, this is the form developed by water, action of river water. So river water always digs below. So that's why you get the narrowing of valley and it gets a V shape. And in the further figure, you will see how a glacier is formed. Glaciers always work like a what you call in Hindi language randa, and a sawmill that crushes the rocks and woods. So glacial valley is always U-shaped. Now you see this is a alluvial fan. Here you can see it here. When a river from the top goes down to the slope, this is how is the spread of the material. So this is called alluvial plain, and these are the marine landform. You get bay, you get lagoon, you get barrier island splits, Tombolo, Caspet. These are different shapes. Now see, I think very close to Jabalpur there is a place called Madan Mahal. You can see there is balancing boulders. Actually, they are having exfoliation from the base, and that base forms a firm stand. And if you have seen that those rocks are lying for thousands and maybe millions of years without getting disturbed. So this is the exfoliation, just like you peel a onion. So and this is biochemical weathering. You can see fungal infection. Now this is leaching, and this structure is developed by wind erosion, just like beautiful window. This part has been eroded by the wind, just as the wind acts like a sandpaper. Again, this is also a typical wind structure. So this top part was more resistant, so it is still wider, but this part was less resistant, so it was eroded more. So you get, these are also structures found in desert, Zeusen and Yardang. I don't want to explain too much. They get this type of ink pot structure, and these are the expansion cracks. When the water freezes and then when it cools at night, it expands. So that is how they develop. And this is interesting picture, biological weathering. You can see maybe in the beginning of the life, this there was a root. Now this has become a big tree. Now slowly it is breaking this rock into two. This is a very good example of biological weathering. We also study the internal structure of the earth in physical geology. You can see this is the top layer crust, and we have mantle, we have core. Just to show you, we have cut a slice. And these are composed of different rock types because of different reason. Like when you go deep, there is something called geothermal gradient. Means the average geothermal gradient is 20 degrees centigrades per kilometer. So if you go down 1 kilometer, temperature is higher by 20. Now can you imagine this to this is nearly 6,371 kilometer. Normally we call it 6,400. But at this level, you know, most of the minerals, they melt and they become magma. So that's why the heavier elements and the minerals which have higher melting point and higher freezing point are found at the lower part. But in the topmost part, we get light colored rocks, which are rich in silica and magnesium. So you can give example, you must have known granites. You can find granites here. And below that, you can find gabbros and basalt, which are darker. Now here, another earth lithospheric structure. Crust, continental crust, lithosphere. This is called lithosphere. And this is an interesting layer, asthenosphere. What will happen if we all are given roller skates, not the shoes, and we are placed on a big moving board? So because of the roller skates, we will all start moving and touching and hitting somebody and colliding with somebody and separating from someone. That is actually this asthenosphere acts as the roller skate for the earth plates. So because of this asthenospheric, this is a viscous layer, semi-viscous layer. So that provides movement due to convection currents. So it form the process of all these geological activities that I will deal with later in the section of geotectonics. Now here, this was I was mentioning. A glacier is a big body and it moves forward. So it start cutting the sides. So that's why glacial valleys, they don't cut downwards. So glacial valley is always U-shaped. Even you see from the space. And if you find a U-shaped valley, you can say that this must have been a glacier action long ago. Now we also study hydrological cycle in physical geology, but it will be dealt separately. There is a specific subject to study the water. Condensation, precipitation, surface runoff, then water goes to sea, then evaporation, that becomes clouds and it rains back. That is a normal hydrological cycle. And there's something like rock cycle. So initially, everything was magma when the earth was cooling. So it cooled, it became igneous rocks. And when the natural agents like water, wind, and air, they acted upon the rocks get weathered and eroded. Then we get sedimentary rocks. And then they get cemented and the sediments, they become sedimentary rock. And when, because of some tectonic activities, they are subjected to heat and pressure, they become metamorphic rocks. Metamorphic rock is a rock that is derived from a pre-existing rock. So to have a metamorphic, you must have a rock in advance. Either it is sedimentary or igneous. So like I give you example, if you had sandstone, it will metamorphose to quartzite. And in our everyday life, we eat lot of metamorphic products. Maybe you did not know, what I can tell you. Even if you boil an egg, you use only temperature and pressure. So the raw egg becomes boiled egg. We don't add any extra component. Same way, the raw potato you can't eat, but when you boil it, it becomes boiled potato. You can eat it. So it is also a example of metamorphism. Just like you put some paste in an oven and cake comes out. So they are all metamorphic products. So in everyday life, we are eating a lot of metamorphic product, like rice also. I found this picture in Mizoram. I like this. Erosion, it explains erosion is the displacement of solids because of wind, water, ice, or any action. Here you see, because of the water action. And no wonder if the water supply becomes more in some million year, this part will become very deep, deep, deep. And then you can get a big valley and big river flowing, and this whole thing will be cut and you will find gorges on both sides. Actually, the similar structure we have in Mizoram. Mizoram. Mizoram is in two parts, northern Mizoram and southern, east and west. And there is a river flowing between. And actually, the whole Mizoram was situated on a anticlinal. Anticlinal means that is hilltop. So the center part was having a crack, and this crack developed water, and ultimately it became a river. And then we have Aizawl town divided into eastern and western. See, this is beautiful. This is the erosional landform made by desert wind. You can see these are sedimentary rocks, and the wind action took this part away. Now you can see a window. Now the second important branch is structural geology. As the name says, structural geology means study of earth structures. So what you see, you will see in the next picture. The rock bodies present on the earth, they get deformed. And then that is study how is the structure and how they formed, and we try to see what causes deformation and what is the further possibility. See this. You can see this here. It is something like you have taken some lot of t-shirts and dresses and you are folding. So nature is folding them. So this is called fold. You can see. And it is obvious because we found when you fold something or press something, it means you are pressing it from both sides, from this side, this side. That is because of compression. And this is called fault. You can see This part has moved down from here. This part has moved down. Again, there's a different type sides of compression, and these layers, they are weak enough, so they break. So they either go down, go sideward, or go up. In this case, it is going down. In this case, it is going up. And in this case, there is no, here you see, this part is moving sidewise. Now, when we drag the rocks under pressure, some part try to react to the pressure. Means shear means you drag something in two opposite directions. So you can see this structure is representing the shear zone. Now there is something called joints. You can see when we make furnitures, we have joints, but in furniture industry, we join them by mechanical or manual methods. But in nature, they are not joined. The joints are developed after they are formed. You can see because of tension. Now, when we have different directions of joint, we get these joint systems. Now, another branch is rock mechanics. To be precise, they study the mechanical behavior of rock. And this is very important because we need to know the response of the rocks. Suppose you are constructing a building, and if you don't know what material you are using and in what environment, if you are living in a landslide prone area or a earthquake prone area like Mizoram, you have to be very careful. Actually, it was a very pity that most of the time in the state of Mizoram, as I spent 10 years there, I will quote it a lot. Most of the urban construction, they did not follow any norm. So that's why we are facing a lot of building collapse there. Now will give you idea.
Scope of rock mechanics in mining. Rock mechanics deals with the properties of rock, which are required for design of underground and open cast workings. It uses special methods for designing these workings. Rock and soil are different from the other engineering materials, so designing them requires special means. While dealing with reinforced concrete, RCC, structures, the engineer first calculates the load which may act on it, and then prescribes the material and design, depending upon the basis of strength required. But whereas in case of rocks, we have to consider the redistribution of the initial masses around the workings made. Since rocks' masses around the underground openings have many failures, the determination of the rock strength is made, depending upon the geological conditions rather than with freedom of designer.
Now here see there are some operations of rock. You can see they are putting rock bolts. Here you can see a lot of joints in the rock. So they will perform their studies and they will see how these joints develop and how they are going to affect. Now you can see the slope is toward this side. So it is a high risk. Now here you see they are doing drilling and this shows analysis. We get core samples from the drilling and they analyze in different machines for different parameters like compressive strength. They keep on increasing pressure on the rock and at some point the rock breaks. That is called compressive strength. And same way they keep on putting tension. So at some stage that the rock breaks. That is called tensile strength. So we check the strength. And they are very useful parameters for further geological and engineering and mining use. And that's geotechnical engineering. So geotechnics is concerned with the engineering behavior of rock material. In this, we go to a field area, we check the number of discontinuities in the rock like folds, faults, joints, what is the strength of the rock and how it is going to behave in future. Now this is very exciting branch of geology, the paleontology. So it is combination of three words. Paleo means past, onto means life, and logi means study. Study of past life. You can see here. I have just put some pictures. These are called trilobites. They were in very old age. Now these are mollusks. This one you can still see today, mollusca, and this is our respected ancestor. This is a dinosaur. These are the plants. So actually, this paleontology helps you to know in which environment a particular rock was found, and wherever these fossils are found, you can date them and you can get their ages. So it is said that the rocks are the books and fossils are the pages. As if you are opening a diary, and these fossils are serving as the page number, like October 26, July 24. But if there is no numbering, you will never know which page was where, especially after the diary is not intact and it's torn. So it's very helpful. Now here you can see in this video.
What do paleontologists do? The word paleontology means to study the history of life on Earth. Scientists who study paleontology are called paleontologists. Paleontologists hunt for and study fossils in order to figure out what life was like millions of years ago. To do this, they look at the origin of where a fossil probably came from, including both the physical location as well as the time period when the plant or animal lived. They try to place the fossil in the environment that existed at the time in order to understand how the life form lived. These clues help paleontologists to better understand the history of life on Earth. We often think of paleontologists as dinosaur experts, and it is true that they are experts in the science of dinosaurs. However, they are interested in far more than just these ancient reptiles. Paleontologists are interested in finding out about all past life on Earth. Some study fossil plants, some study fossil fish, some study fossil mammals, and some study dinosaurs. Paleontology is a combination of geology, which is the study of rocks, and biology, which is the study of life. Thus, paleontologists have to be experts in a lot of different things. Everything we know about the history of life on Earth is thanks to the hard work of these paleontologists.
Now here you see, I have collected these pictures. Now you can see these, actually what happens when the animal dies. It somehow, and an overlying layer comes and they are preserved in the rock structure. But when they are preserved, obviously the hard part, that is the skeleton, remains unaltered, and it is even further protected by a chemical coating, just like we put nickel and chromium plating to protect from rust. Now here you see, this bone must have been white, but it is protected by a iron rich solution. Now here you see this whole fish is preserved, a hard part. Even you can see these are trilobites. They are called trilobites because they have three lobes. This part is called cephalon, this is called thorax, and this is a tail that is called pygidium. Now you see, entire dinosaur is preserved. To add some funny pictures, you see, that is what our ancestor, that is called Ramapithecus, Shivapithecus, ape man of Java, Cro-Magnon, then modern man. So a little bit of humor here. This I found very interesting, so I took it. I don't know who created it, but it is like, you see here, man and ape. They can mock US president the way they are mocking our Indian prime minister. Now we have another branch, stratigraphy. It's a nature book of Earth history, just like the diary of Earth. If you see in the title picture, it is stratigraphy, stratified layers, study of rock layers. Primarily, it was made to study only sedimentary rocks because it was really believed that only sedimentary rocks are layered. But now we know that even igneous rock can be layered. Now you see the same picture comes again. So If you consider here, you can see this is a thick layer. Thick layer means this certain environment prevailed for a longer time. So the thickness tells you how long was the period. Then if the place is not disturbed, you will get a second layer above that. And this one is younger, this one is again younger, younger. And you can see this hole. And the sedimentary rocks tell you about the environment. If you have very big unit of sandstone, it means that this was under a shallow marine condition. But if you get lot of layers of dark colored fine grained shell, it means these kind of rocks are only found in marine environment and even deep marine. So you can see this represent that this part was under influence of a ocean for millions of years. But unfortunately, we don't get this kind of fortunate sites. Mostly what happens when this was there and a compression comes and they become folded like this. If they got disturbed, they can be folded or they can be faulted. But we are lucky in Grand Canyon, we get everything intact. So this is what we study in stratigraphy.
Sediments and other materials are deposited on the Earth's surface in layers. Archaeologists study these layers, or strata, to understand how sites formed and to determine the relative ages of the artifacts in the layers. This study is called stratigraphy. Archaeologists interpret strata according to the law of superposition. This law states that the layers deposited first are the oldest, found at the bottom of a site, while the layers deposited most recently are the youngest and will be found at the top. Consider these three books. If I stack them one at a time, the book I set down first ends up on the bottom, the book I set down second ends up in the middle, and the book I set down last ends up on top. Now pretend each of these books represents a layer at an archaeological site. The materials found in the bottom layer were deposited first, and the materials found in the top layer were deposited last. The first visitors to the Hardaway site probably left trash and other evidence behind, like these projectile points. As natural and human-made debris accumulated over thousands of years, it eventually covered the traces of these first peoples. Other groups visited the Hardaway site, made new stone tools, and left their old ones behind. More debris over time eventually covered these artifacts and helped to preserve them. When archaeologists excavated the Hardaway site, they found 4 distinct layers. They interpreted the artifacts in the uppermost layer as the youngest and the artifacts in the bottom layer as the oldest. Today, archaeologists are still studying these artifacts to understand what people did at Hardaway at different times in the past.
Now here I put some pictures. So this is very interesting. This is called correlation. See, suppose you got this kind of fossils in a certain part of the world. And if you find the same fossils in different part of the world, we can correlate that, okay, they were same together. They were similar. They had similar environment. Maybe they were united together. So this correlation has given the basis for the idea of plate tectonics. On the basis of fossil remains, we have concluded that India, Madagascar, Antarctica, South Africa, and Australia, they were once united. And now later on it is proved also. Now here you see it's a layer, stratigraphy layer. And these are the principle of stratigraphy. This was explained. Order of superposition means what comes top is the younger. And original horizontal means initially everything was deposited horizontally. So there are many theories. Now here you see life through the ages. So these are the geological calendar. Archean, Proterozoic. Proterozoic means primitive life, and this is called Paleozoic means primary life. Mesozoic means intermediate life. Cenozoic means tertiary life, and we are here in Holocene. And this is how in the video it was explained how the profile is found. Now this is the idea of geological time scale. So as a human, we should not be very much proud if the earth is, our history is like an apple, so we are just even smaller than the apple seed. We are very minimal, we are giving very minimal contribution to the earth yet. Now here you see primitive fishes, then early reptiles came, and then at the end of Paleozoic life, these trilobites, those three-legged animal disappeared. Then earliest dinosaur came, mammals came. Then at this time, Jurassic and late Cretaceous, dinosaurs were extinct because of a meteoric impact. And that's why the movie Jurassic Park has made them very famous. The dinosaurs must thank Steven Spielberg. Now you see, the modern human came here, now we are here. Now another branch is mineralogy, study of minerals. So minerals are what? Natural components formed through geological process. And like everything that is mostly combining, like sodium chloride, even the salt is also a mineral. It is combination of sodium and chlorine. Like a sandstone is a rock also, but when it is in mineral form, it is called quartz. SiO2 is the chemical composition. So they are minerals. So we study a lot of minerals, and there are different mineral groups. And each group has a definite property, definite type of structure, definite pattern of chemical composition, and definite structure of silica and oxygen. That is called silicon oxygen ratio, because most of the minerals are silicates. And that is beyond the purview of this lecture. Now you see, there are some pictures of different minerals. And these kind of minerals, they are used as gemstones. Now you see, this is a pure quartz. Pure quartz is transparent, but when it is having impurity like chromium or something, it becomes green. Now you see, this is another branch of mineralogy, geology, that is called crystallography, means study of crystals. So some minerals grow as beautiful crystals, as you can see. And these are not artificial, these are the natural crystals. You can see, this is also a crystal form. It's in the form of a flower. Now you see, here it is showing that all crystals have definite structural pattern. Now here this one is isometric or cubic, for example. You must have seen when you play Ludo, we have a dice. Dice is a cube, six-sided cube, the number is 10. So some of the minerals which formed in cubic system, they always have all their dimensions same. A good example is galena. You can see it's here. And some are like this. One axis is long, so they get orthorhombic. You can see here. Now petrology. So Latin word petros means rocks, study of rocks. And rocks can be of three types: igneous, sedimentary, and metamorphic. Igneous is the most basic primary rock, means when earth was forming, everything was magma. So when the cooling of magma started, we get the first type of rock, they are called igneous. And when these rocks are weathered and eroded, scratched, you can say scratch something, and then it is deposited somewhere, then it becomes sedimentary rock. And then either igneous or sedimentary, when they go under temperature and pressure, they can change their shape and texture, everything. That is called metamorphic rock. You can see.
Good morning, everyone. Today, we will discuss about metrology. First of all, what is metrology? It was derived from the ancient Greek word petros, which literally means rock, and logos, which means giving it form or meaning. Petrology is a scientific study of rocks that deals with its composition, texture, and structure, their appearances and distribution, and its origin in relation to physiochemical conditions and geologic processes. It is concerned with the three major types of rocks, which are igneous, sedimentary, and metamorphic.
It also includes the subdisciplines of experimental petrology and petrography. Experimental petrology involves the laboratory synthesis of rocks for the purpose of ascertaining the physical and chemical conditions under which rock formation occurs. Petrography is the study of rocks in thin sections by means of a petrographic microscope. It is primarily concerned with the systematic classification and precise description of rocks. Petrology relies heavily on the principles and methods of mineralogy because most rocks consist of minerals and are formed under the same conditions. Also essential to petrological research is the careful mapping and sampling of rock units, which provide data on regional gradations of rock types and on associations unavailable by other means. To sum it up, here are some key aspects that we must remember in tackling about petrology. First of all, petrology is determining the official name of a rock based upon observations in the field, in hand sample, and under the microscope. Petrography is using polarizing light microscope to investigate textures and mineral assemblages of rocks. Geochemistry is the application of chemical analysis to understand the physical and chemical processes that created the rock. Geochemical analysis include whole rock major, minor, and trace element geochemistry, compositional analysis of mineral or glass, magma phases, radiogenic and stable isotope geochemistry. Experimental petrology is creating or modifying rocks in a laboratory setting under known conditions to provide a framework for understanding the thermodynamics, geochemistry, and petrography of natural rocks.
That would be all for the introduction.
Now here are some examples of the rocks. Like this is a granite, and this is gabbro, and this is basalt. These are igneous rocks. This is formed under great depth, these two. That's why they are very coarse grained, because they get enough time to cool. And this one is fine grained. Now here there are example of sedimentary rocks, so common. You all have seen sandstone, limestones, and shales. And when this shale get metamorphosed, it becomes slate. And when this sandstone gets metamorphosed, you get quartzites. So here we are getting, I gave three rocks, schist. They are all oriented in the same direction. They represent some pressure and temperature under a guided direction. And this is called gneiss. You can see alternate colored bands. And this is a mylonite, means these kind of rocks are formed along the margins of plate collision where two plates are rubbing each other. So the softer ones crush and those which are high resistant, they remain as big boulder. They are called eye, or in Latin they are called ogen. Now this gives you idea of metamorphic phases. Along this line, you see pressure is increasing. So this will show mostly impact of pressure. Here along this line, most of the rocks are metamorphic, which are only under the influence of high temperature. And along this line, they are under the effect of both temperature and pressure. That is called regional metamorphism. These are some pictures and thin sections. Now this is very important, economic geology. So it is the geologist or earth scientist who discovers the location of important economic minerals. Like to quote in Botswana, is based on the economy based on diamonds. So we have a lot of diamond mines and even gold and nickel and chromium. And let me tell you, recently a diamond mine Lucara has discovered the world's largest diamond here. I forgot, I could have quoted it here. Now this is how we do in economology. We look for ore, and ore is what is the difference between ore and a mineral? A mineral is even ore is also a mineral, but ore is a mineral with some economic importance. Like example is if you say hematite is a ore of iron, Fe2O3. So, and magnetite is Fe3O4. So they are economic because they are iron ores. Now another branch is geophysics. The principle is the study of Earth and its environment and space on the basis of the physical properties. The very simple example I can give you. Suppose if you dropped your key ring or an important key in the sand, what is the best way to find it out? If you try to go and look just by your eyes, it will take maybe many days and you still can't find. But if you come with a magnetic plate and you move along with it, because your key has a magnetic property, it will come and stick to the plate. Same way, if you are looking for a copper deposit, so obviously the copper has a high conductivity of electricity. So then we conduct electrical survey. So where there you have copper deposit, it will show high value of conductivity. Same way, if you are looking for coal is very high in resistivity and same way very low in conductivity. So these properties can help you, and coal has a low density also. So we combine density. If you are looking for a radioactive element, it has radioactive property, then we use radioactive methods. Like we use a Geiger counter and it can sense where there is a radioactive material. I gave you simple examples.
Have you ever wondered how we know what the inside of our planet is like, even though our most advanced drills barely scratch its surface? Or why some places have earthquakes or auroras, but others do not? To investigate those questions and others like them, scientists study geophysics, one of the major branches of geoscience that applies the principles of physics to the study of the Earth. Geophysicists connect the physical processes that we see and experience on the surface of the Earth, like earthquakes and volcanoes, to processes driven by the Earth's interior properties or affected by oceanic, atmospheric forces. Geophysicists examine what's inside the Earth at large and small scales, conducting surveys and generating maps of Earth's physical fields, often without disturbing the surface. What does that mean? Some geophysicists install instruments called seismometers to study earthquakes' impacts on people, as well as what earthquakes can reveal about Earth's internal structure and composition. They can create numerical models to measure and forecast how the ground might behave in a future earthquake. Some geophysicists use satellites to understand the Earth's changing shape and gravity field, such as the Global Navigation Satellite Systems, including the Global Positioning System, or GPS, which people use to navigate. Many geophysicists use probes carried by ships, boats, or land rovers to scan for useful resources such as groundwater, metals, and hydrocarbons. Others use them to evaluate human impacts on water quality or to work with emergency management teams for mitigation and planning around natural hazards such as tsunamis, volcanoes, and landslides. Some geophysicists use a combination of these tools and techniques to focus on big picture ideas in science, like visualizing and explaining how plate tectonics functions, how our magnetic field protects us from the sun, or how climate change has and may continue to affect our planet. Together, all of this work shows how geophysics is a dynamic, innovative field that seeks to answer many of the most fundamental questions about our planet and how we can live on it safely.
Now this is when still it is related to geophysics, but they separate the study called seismology, study of earthquakes, and seismic waves means earthquake waves. So there are primary and secondary waves mostly. So those are the earthquake waves, and we study how they can travel. I cannot go in details, it is already 1 hour. Now you see, this is how the earthquake waves are traced. Whenever earthquake takes place, there is a focus, means from where the earthquake originated, and there is a epicenter. Epicenter means the center on the surface. So now you can see earthquake waves, primary and secondary. Some, they do not travel inside the liquid. So even they can, seismic waves can tell you about the structure of the earth, where we have solid, where we have liquid. Here are some images. You see here, they are showing different intensity zones shown with different colors. So now here you see they are using artificial earthquake, and when they are going and hitting back, this is called seismic reflection and seismic refraction, two methods. They can give you the idea. Different layers will show different rate and different pattern of rebound. So that is how we discover ore bodies and even oil. Now geochemistry is like a chemical principle to deepen the understanding of the earth. So just earth is like a experimental jar. So because of the action of water, wind, temperature, pressure, and gases, and changing depth, earth is always acting as a chemical laboratory, and amazing things come out due to the geochemical process of the earth. Here are some clues.
Until now, you've probably learned a lot about how chemistry works in the lab. For example, in this flask here, we have some compounds in solution. Reactions can also happen in the gas phase, or even the solids at high temperatures. We can think about all of the chemical equations and principles which govern what's going on. But that's not the only way we can use chemistry to understand things. Take a look at the whole Earth now, for example. The The Earth is a huge chemical flask with many processes going on all at the same time. Here's a periodic table showing the relative abundances on Earth for all of the elements. Obviously, not all elements were created equally. But why? What happened? Or consider this graph, which plots the Earth's average temperature over the past millions of years. How can we go back in time and measure this? Well, we can't. We need to look for the right chemical clues and know how to interpret them. So many of the chemical and physical principles that we've learned can be applied to the numerous questions out there. So in this course, I'll show you some of these examples. Then we'll take a look at some global or even planetary issues from a chemistry perspective. I look forward to seeing you in the Introduction to Geochemistry.
So here are some symbolic pictures to show how geochemistry works. Now in this geochemistry, we also study as a knowledge of how the solar system, and even in our syllabus, we have origin of solar system and universe. So this is how solar system formation for the gas cloud. And if you remember in my earlier lecture, I have presented that all this knowledge was mentioned in our Veds, and they are corroborated to the current day knowledge. Supernova explosion. And that is how this is referring to the Big Bang theory, planetary formation, and how the solar system formed. Now, so we can add, there is a separate branch, sub-branch of geochemistry called cosmochemistry, but here cosmology is a entirely separate subject. We study the entire universe.
Today we'll learn about cosmology, not to be confused with cosmetology, but we'll study how the universe formed and how it will end. I'm your instructor, Tony DiBernardo, and welcome to my channel, Space But Messier, where you'll learn everything you need to know about spaceflight and astronomy. Cosmology is the study of the large-scale properties of our universe as a whole. This means that cosmologists will look far into the past of how the universe was born, all the way to how it will die. They look billions of years into the past to the edge of the observable universe to see how this whole universe was created. They also test modern theories of physics to determine how it's going to die. What is the fate of our universe? Well, scientists have built instruments to test this. For example, NASA and ESA's Hubble Space Telescope may be known for its incredible images, but did you know that its primary mission was cosmological research? While we still have a long way to go, Hubble has greatly improved our understanding of dark energy and the nature of the expanding universe. Another great discovery came from NASA's WMAP, or the Wilkinson Microwave Anisotropy Probe, which mapped tiny fluctuations in our cosmic microwave background, that ancient light left over from our early universe. And it discovered that familiar atoms only make up 4.6% of our universe, and dark matter makes up 24%. This means that everything we see accounts for less than 5% of our universe. So if you're curious about what came before the Big Bang, what exactly is dark energy, and what will happen to our universe when it dies, then cosmology is just for you. Now, if you like this video and you want to see more like it, please subscribe to this channel or send it to a friend. If you have questions.
So here are some symbolic pictures, what we do in cosmology. Now this is a separate study called hydrology. We have mentioned hydrological cycle, but a study and distribution of movement of water both on below and surface, that is called hydrology. Like when you are discovering a water body, so you know water, underground water, if there is no cap rock means there are some impervious layer beyond which the water cannot go down. So that becomes the reservoir. Otherwise, the water will trickle down. So there are several methods to study hydrology. You can see here. These are subsurface where we can find water. So that is how hydrologists work. They can even discover water bodies. And mining geology. So mining geology combines economic geology and mining engineering. in simple terms, how to explore and exploit the economically important minerals. Like in Botswana, we are doing diamond mining, gold mining, chromium mining, and if even coal mining, and it can apply to anything in any part of the world. Wherever you do the digging, that is a scientific and politely technical word for digging, that is mining. Now we have moved far beyond the word digging. Now we have advanced technologies under mining engineering. Now, and we are using a lot of softwares to develop a mine and then design the mine plan. You can see the same in this interesting video.
So you've been working long and hard for a while now, searching for a solution to a problem you can't solve. Friend, just let me introduce you to this beloved institution. He'll help your mining skills evolve. Cause technologically speaking, he's the real deal. You won't have to beg for steel. He's the mining geologist, here to show you all the things that you might have missed. He's got plenty of software tips and tricks for your geoscience lives. So you got your fingers in mining, exploration, and mining engineering and information. And check the links that you'd like. Subscribe.
You see, this is a mine in Botswana, and again this one. And this is the mine model developed through software. This is me in a mine. I think it was a nickel mine in Sikkim, and that's my student. Now he is a assistant professor in Zirtiri College, Aizawl. And oil exploration, even as we mentioned, oil exploration is again exploring minerals. Engineering geology, application of geology to engineering study. For example, location, design, construction, operation, material. Suppose if you have to build a dam, so you have to consider what kind of rock foundation we need, whether the area is under the influence of earthquake or landslides. So it can cause huge havoc if you build a dam at a wrong place. So we check a lot of things: geology, structure, stability, connectivity, and the use pattern. Like this was taken, this was a dam on Tista River. I took this picture while I was coming from the Sikkim fieldwork. Now you see, geological engineering, civil, mining, petroleum, environment. We actually, all these are intermingled. You cannot separate one from other. Now here in this picture, you can see there is a tunnel going in, and you can see the rocks. If you can use your imagination, you can see that this is a convex anticlinal body. So if it could be complete, means you get this kind of cap structure. So as you can see, tunnel is here, and all the rocks are dipping away from the tunnel. So this kind of tunnel is safe. Imagine if the rocks were coming like this from both sides, that tunnel would not be recommended. So that is just a simple example of. Now again, you see, this is a bridge in a permafrost region. Now in the foundation pillar, it must be located in a stable surface. You can't make a pillar under a muddy layer or something that can flow. So the whole bridge will collapse. So that is also a part of engineering geology. Now geotectonics means action of tectonic forces on Earth. You can see here. Here you will see a lot of animations. See, this is our Earth, and this is the animation of plate tectonics. You can see how the plates are moving, and this is India in the corner. It is going and colliding with Eurasian plate. Now you see again in this animation, you can even see these numbers. They are telling you the age. When you see the current, it is showing this position, and this is Himalaya. So there are major lithospheric plate, and as I told you, they are floating on the asthenosphere. Now these are the geotectonic units of the Earth, and there are some interesting area. These are shield areas. They are supposed to be stable, and there are some movement. And this, wherever you get the collision of plates, you can get mountain. This is whole a mobile belt. This is very mobile, and this whole area experiences lot of earthquakes and volcanism. You can see here was the Mizoram. So we feel, anybody see this is Andaman Nicobar. We get lot of earthquakes, even here in Indonesia, anywhere. This I mentioned earlier. Similar fossils in South Africa, Antarctica, South America, and India. They gave the clue that those, even in Antarctica we have lot of coal deposits. Now can you believe Antarctica is all frozen? So, and coal is from vegetal material. So how there was a huge amount of vegetation in Antarctica when it is so cold? So it shows that there was a time when India and Antarctica were either in the northern hemisphere or the Antarctica has moved there. Because there was a time that surely Antarctica was having a warmer climate. So this is also combining paleogeology, paleogeography, and plate tectonics. Now you see, this is interesting. You can see these are the evidences of plate tectonics. You can see here, this is called jigsaw fit. This South America, North America, this is Africa. And if you can visualize, just break a Parle-G biscuit, and then par will be in your left hand and lay will be in your right hand. Something like that. So if you try to fit, you can see that just like the puzzles we used to play in our childhood. Make the blocks and join the horse, join the elephant, and join the India map. Same thing. You can see this notch can fit here, this notch can fit here. So it means there is called juxtaposition. So there was a time when they were united, and when they were united, you can see I gave you the example of the biscuit Parle-G. If this hole is Parle-G, so when you break the biscuit from center, par is here and le-G is here. Something like that. So they are following the same structure, same age, everything is the same. So how it is possible? That is the clue. Now you see, this is an interesting picture. If you remove all the water from the earth, this is what we get. This is South America, North America, this is Africa. And you see this whole elevated, that is called mid-oceanic ridge. From there, the plates are separating away. That is called divergent margin. So it almost covers the whole globe. You can see this starting from near polar, going down to equator, and then going to south. And this moves this side. So these all areas experience a lot of volcanism. So how it takes place, you can see here. You can see this is what happens. This magma comes up under the sea floor, and then you get a lot of ridges because they immediately cool, because they come from a very high temperature and they collide with a very low temperature regime below the oceans. Now you see, this is what happens. I said asthenosphere, how the plates move. You can see when any material cools, it becomes heavy, it goes down. And then it is heated again, then it again goes up. So you can see this side is going up, this side is going up, and then again this is moving this side, this is moving this side. So it is something like two people are sitting on two chairs and somebody is dragging their chair away. So that becomes divergent margin. And when these two chairs are keep coming close, you get a convergent margin. There is the case of Himalaya. Now this is showing how the arrows are showing average rate and how each plate is moving. So you can see this plate is moving this side, this is moving this side, this is moving here, and this is in Australia Indian plate. This was going here, and now it's here. And there are three main types of plate boundaries, as I said. One, they come closer, that is convergent. One, they move away, divergent. And third one is they just slide past each other, saying bye-bye to them. So the good example is that San Andrean fault of this. Now you can see what is happening here. Red Sea is spreading, Arabian Peninsula is spreading, this is also spreading. So Red Sea is used as a gulf and it's a canal. In future, after a few million years, this whole thing will separate and we will get a very big ocean. And this thing will close. So that is how life is. And same way Himalaya was formed. Where we have Himalaya, there was a very big ocean called Tethys. So because of the plate, Indian plate moved to Asian plate, Eurasian plate, that big ocean closed. So we got a very big geosyncline in which Himalayan sediments were deposited. Now this is what happens. These are the continents. Now because of the heat supply, the central parts become baking and cooling. Even if you bake coal, after some time the coal becomes ashes and they become very weak. So this will explain you see, this central part will collapse. Now you got a rift valley faults, and we also have rift valleys in India, like our Narmada river, Narmada, Son, Mahanadi and Godavari. They are all flowing in the rift valleys. Now you see, this is what happened at the end. This is how collision of Indian plate, and this used to be a big ocean, Tethys ocean. You see the blue one. Now it has closed. Now we've got Himalaya. Now you see, this is very interesting. This plate is going down. This is called collision. So what is happening? If this plate is going down here and this both are ocean on the top. So you know what is happening. This plate is going down, and after 100, nearly 100 to 200 kilometers, geothermal gradient becomes too high, then the plate material begins to melt. And when it melts, it goes up and bumps here. Bumps here. It is the similar example. There are a lot of ladies sitting in the audience. So I can see, if you sometimes you try to make, we are all Indians, we know how to make pakoda. So when you put the besan in the kadahi, as long as the kadahi is cool, that besan lump will be sitting at the base. But the moment kadahi is heated, that besan will rise up. That pakoda will rise up. So actually, God is making pakodas, and those pakodas are hitting the islands. Like the good example is Japan. That's why in Japan we experience a lot of earthquakes. So plate tectonics is a very good discovery. Maybe in earth science, one of the best discoveries apart from GIS. So it explains everything, how mountains will form, where you can get volcanoes, where you can get earthquakes, where you can get Rift Valley trenches, mid-oceanic ridge, where to find minerals and ores. Because when the magma is, when the mantle is exposed, lot of hidden resources come up. Like one example is diamond. Diamond is placed under a very high pressure condition under great depth. But when it is cracked, it immediately comes up in form of as like a bullet speed. Now here it is the paleogeography, study of historical geography, physical elements, something like covered in plate tectonics. See, this was how we were. Now you can see Africa and America are together here. Now you can see now they are separating. We have Atlantic Ocean. Now you see this is separated. And this is India. And this is Pacific Ocean. India is going here and colliding with Eurasian plate. And now we are getting Himalaya here. You see, this is where we get Himalaya. Again, let's move faster. We are getting too much time. So this is paleoclimatic evidences of continental drift. You have seen in the last. Now disaster management. This is very, very important for human life. And there is something called hazard and disaster. Hazard means something happening naturally. Like if you go in mountainous region and Himalayan region, lot of rocks fall every day. So that is a hazard. But when if a rock fell and then some people are killed and some buildings are damaged, then it is called disaster. Okay. Now you see tsunami. Tsunamis are submarine earthquakes. It is something like that when the deep sea rocks, they fall under landslide. So the whole surface jumps. You can even try at your home. Take a glass of water on a table and hit the table hard. You can see the water in the glass will begin to jump up. That same thing is tsunami. God is hitting the table. You can see this. You must have seen a lot of movies and videos on tsunamis. This is Earth's landslide, earthquake. This is an example of Mizoram where we used to have frequent landslide. Every landslide comes, we used to visit. You can see the half of the road is gone. And here it is cracking. This is about to go. And then local volunteers called YMA, they come to rescue. And then is volcanology, study of volcanoes.
This video is looking at one of nature's most wondrous and amazing natural phenomena, volcanoes, and looking at the subject of volcanology and what is included in this amazing subject. This is the Earth Science Classroom. Volcanology is the scientific study and discipline of looking at volcanoes. Now, volcanoes can be the actual volcano, the edifice, the shape, the profile, different types of volcanoes. It can also include the magma and the interior workings of the chamber and the composition of the magma and how it's going to cause and create different volcanoes. We're looking at the eruption style, the eruption features, the characteristics of the volcano, the geographic location of the volcano and how it's formed through various processes in the Earth's interior, whether it be subduction or a mantle plume or other ways to melt and assimilate magma and bring it to the surface. And you have these amazing natural phenomena that are going to erupt in different time periods, in different frequencies, and in different sizes. Some volcanic eruptions are small and effusive and have just gas release, or some nice basaltic lava. Some eruptions are huge and cataclysmic and change the world's climate and change the world's as we know it in terms of human society. This subject is so diverse and beautiful, and how it all comes together under the term volcanology. So volcanology is a scientific discipline that combines all branches of classic physics, classic chemistry, and classic biology, ecology, evolution, and how also the volcano can impact climate and climatology, and looking at paleoclimatology, looking at the atmospheric composition, because the gases that are released through eruptions, with the greenhouse gases, with the water vapor, with the CO2, NO2, SO2. So all these different entities of science can all be discussed and looked at through volcanoes and volcanic activity. And even discuss the Earth's history going back 4.6 billion years, and how and why and where volcanoes played a huge role in shaping and forming our modern day planet. I hope if you go into this yourself and look into the subject, you love it as much as I do.
Now here volcano, you see lava flows. Some lavas they flow, they don't erupt. Mostly basaltic lava because of the high viscosity, low viscosity they flow. And this is lava they flow. Now this is interesting. You see, these are based on the plate tectonics model. You can see this belt. This belt, because of tectonic activity, we experience a lot of earthquake, and the same time, the belt of fire, that of volcano, is coincides with this. And now we are coming to geography. As I described in the beginning, geography is the external feature study, and it includes everything. Means human geography, economic geography, physical geography, blah blah blah. So here is a view of different branches of geography. We have economic, social, political, cultural, biogeography, climatology, soil geography, mathematical geography. Oceanography is the study of the ocean. Here you can see chemistry, physics, biology, and geology. They are all combined in oceanography. Here are some interesting pictures. Marine geospatial research, ocean fauna, biological oceanography. Mysteries of ocean, they can be solved by study of oceanography. Now this is something related to oceanography, but it is focuses on the history of the structure of the ocean floor, that is marine geology. And there's meteorology. This is very important. You always see when you watch news, you see weather forecast when cyclone is moving from Kerala coast and hitting Tamil Nadu coast. So those are coming under meteorology. I have to be fast. Weather and climate, physics and life, you can see. Now we are coming to environmental geology. That is one of the greatest debates in the modern times, because we are developing at a very fast rate, and then we are producing too much of harmful gases and sanitation waste and dumping waste. So this study deals with the interaction of human with their fundamentally geological environment. So main aspects are climate change, human impact, atmosphere and climate, global warming, groundwater contamination, pollution, human-made dam impact, mining environment impacts, impact of all human actually activities on the nature. And pedology, when we focus on the understanding and characteristic of soil formation. So these are some pictures that share where you do the analysis of soil. You can say clay soil, loamy soil, silty soil, sandy soil, and more. Civil engineering, design and executing is a structural framework. We have to move very quickly.
Dive straight into the world of civil engineering, a discipline that shapes our physical environment. Civil engineering is all about designing, constructing, and maintaining the physical and naturally built environment. It's the reason we have roads to travel on, bridges to cross rivers, canals for water transportation, dams for water storage, and buildings to live and work in. This discipline is not just about structures, but about shaping the world around us. Civil engineering is the cornerstone of our built environment, making our daily lives safer and more efficient. Civil engineering is a vast field encompassing various sub-disciplines. Each one focuses on different aspects of our built environment, helping to shape the world around us. First, we have structural engineering, the backbone of our cities. It's all about designing and analyzing structures like bridges, buildings, and tunnels to ensure they're safe and stable. Next up is environmental engineering, which combines science and engineering principles to improve the environment. It's their job to solve issues like air and water pollution. Then there's geotechnical engineering, which studies the behavior of earth materials, informing the construction of foundations, dams, and roads. Transport engineering is about designing and managing transportation systems to boost efficiency and safety. Water resources engineering focuses on the collection and management of water, whether that's for drinking or irrigation. Lastly, we have construction engineering, which oversees the planning and execution of designs, turning blueprints into reality. Each subdiscipline of civil engineering plays a critical role in shaping our world, contributing to our society's development and progress. Civil engineering is an exciting field full of opportunities to create, innovate, and make a real difference in the world. It's a profession that shapes our daily lives, from the roads we travel on to the buildings we live and work in. Every project is a chance to touch countless lives, to contribute to something tangible and long-lasting. The satisfaction derived from seeing your designs come to life is unparalleled. Start your journey in civil engineering today and leave your mark on the world in an enduring and meaningful way.
Here are some symbolic pictures of civil engineering constructions. Now this is the modern techniques of, we started with going to the bush and going to the field and taking the rock samples and soil samples And this geospatial technology has really made our life easy. So this includes photogeology, photogrammetry, remote sensing, and LiDAR. LiDAR is the latest one. So here actually we use GIS, that is called Geographical Information System, and they have this global positioning system, GPS. We also have all GPS in our mobile phones. So let's see how it works. There are two types of satellites. One is geostationary and another one is polar. So geostationary means it moves with the speed of the Earth. So in relation to the relative speed is 0. So it is always stationed over one particular point where it is installed. And the polar ones are moving along the pole from North Pole to South Pole, and the whole Earth passes. So polar satellite can take pictures of different parts of the Earth. But these geostationary satellites are country specific. They take the pictures of only a specific part. You can see here. Now you can see this one is focused on South America. So it is always taking pictures of South American part. The panel is picture panel is the same. And what the area that is it covering, it is called footprint. A near polar orbit include a small angle with the respect to the Earth rotation axis. And you see this is the polar satellite, low Earth orbit. You can see the whole Earth is passing and it is taking the picture of the whole. It travels north-south direction. Now this is how its technology was. Communication, you can see with the flow chart. For the remote sensing, we use the sunlight. We study the reflection of different material from the sunlight. You can see here. Energy source is the sun. Different spectrum, and then it is radiation coming to, and these are the reflection. And that reflected data goes back to the satellite. And there you see different color bands are there. So they are sending it back to the Earth station. And then on the basis of those images, they generate image. They can be physical layer, they can be urban layer, they can be forest, whatever. So, and when at the same scale, when they combine, that is called sandwiching. Suppose there is a geological unit layer, and then we have an urban layer. So when we switch them on the same scale, you can see in which part of the town, which rock is there. Something like that. And there is airborne survey. You are taking pictures from an aeroplane. And in the beginning, when there was no aeroplane, scientists were taking pictures through the balloons, hot air balloons. That was also airborne survey.
Hello and welcome to today's video where we will be discussing Geographic Information Systems, or GIS for short. GIS is a powerful tool used in a variety of fields to collect, store, analyze, and visualize geospatial data. In this video, we'll provide an overview of what GIS is, how it works, and its applications in various fields. Without further ado, let's get started. What is GIS? GIS is a computer-based system used to capture, store, manipulate, analyze, manage, and present spatial and geographic data. It is a tool that allows us to visualize data in a geographic context, providing a better understanding of complex data. GIS combines data from different sources, such as satellite imagery, maps, and other geospatial data, and transforms it into meaningful information that can be used for decision-making. GIS comprises three main components: hardware, software, and data. The hardware component of GIS includes computers, mobile devices, GPS receivers, and other equipment that enables the capture, storage, and display of spatial data. The software component of GIS is the suite of programs and tools that allow users to manipulate and analyze the data. The data component is the actual geographic data that is inputted into the system. How does GIS work?
GIS works by collecting geospatial data from various sources and integrating it into a digital format that can be analyzed and visualized. The data can be captured using various techniques such as remote sensing, GPS, and surveys. Once the data is collected, it can be analyzed to identify patterns, relationships, and trends. This analysis can then be used to make informed decisions and predictions. GIS uses a variety of analytical tools to analyze and visualize data, including geocoding, data mining, spatial analysis, and modeling. Geocoding is the process of assigning geographic coordinates to data, such as addresses or place names. Data mining involves extracting useful information from large data sets. Spatial analysis is the process of analyzing the relationships between different geographic features. Modeling involves creating a representation of the real-world situation in order to make predictions or simulate outcomes. Applications of GIS. GIS has a wide range of applications in various fields, including, but not limited to, environmental management. GIS can be used to monitor and manage natural resources such as forests, water bodies, and wildlife habitats. It can also be used to track the spread of invasive species and monitor the impact of climate change. Urban planning. GIS can be used to analyze the spatial patterns of urban areas, such as population density, land use, and transportation systems. This information can be used to make informed decisions about zoning, transportation planning, and emergency management. Emergency management. GIS can be used to track natural disasters such as hurricanes, earthquakes, and wildfires. It can also be used to analyze the potential impact of disasters and create evacuation plans. Business. GIS can be used in marketing to target specific demographics, analyze sales data, and identify potential new markets. It can also be used to optimize supply chain management and site selection for new stores or factories. Agriculture. GIS can be used to manage crops, monitor soil conditions, and track weather patterns. It can also be used to analyze crop yields and predict future yields based on environmental factors. Geology. GIS can be used to map geological features such as rock formations and mineral deposits. It can also be used to analyze the impact of natural disasters such as earthquakes and landslides. Transportation. GIS can be used to optimize transportation routes, analyze traffic patterns, and plan new transportation infrastructure. Conclusion. GIS is a powerful tool used in various fields to collect, store, analyze, and visualize geospatial data. It allows us to better understand complex data by providing a geographic context. GIS has a wide range of applications, including environmental management, urban planning, emergency management, business, agriculture, geology, and transportation. With GIS, decision makers can make informed decisions based on accurate and up-to-date information.
Now, these are the video has already explained, but we can do all those things through remote sensing and GIS. Hazard zonation. This I want to focus. Suppose we are suspecting, like we know that Himalaya is rising at the rate of 12 inches per year. So how do we know that? Because we have put stations, and every time when it is rising, the accurate elevation is measured. And if some places we are suspecting tectonic movement or fault, so along the fault line we put sensors on both sides, so that can also detect how much the stations have moved. And photogeology is something like when you take photos, aerial photos, study of them is called photogeology, and photogrammetry is the measurement of those photographs. So when you take photographs to photogeology, and then you can see some examples here. And there is something overlap. When you take two pictures, they do overlap of 60% to combine the images. And we use suitable flight timing. And that is how we have a stereoscope to measure. Now, this is a very advanced technology, light detection and ranging in LiDAR. That is the most precise application of GIS, remote sensing, and photogeology. And you can see here how we get very perfect images to the accuracy of few inches.
Airborne LiDAR is a technology that was developed in the last 10 or 15 years, which involved flying a laser-based instrument in an aircraft at relatively low altitudes, and then fire laser pulses at the ground or other surface to produce a very high-resolution model of the Earth's surface. It reveals to us a new image of the surface that we can't obtain in any other way. It takes our previously blurry view of the Earth's surface and brings it really into sharp relief and sharp focus, which allows us to make fundamental advances in what that shape of the Earth tells us about geologic processes.
With the help of the state of Texas, or the State Geological Survey, we purchased the most advanced LiDAR system in the world. It has 5 sensors. We can shoot an image down through water. We've flown the North Slope of Alaska last year and are collecting data now that gives you resolution that's at the inch by inch or a slightly larger scale from the air. So we're literally able to resolve the surface of the Earth at a resolution space that's never been seen before.
LiDAR has been used to detect archaeological sites beneath tree canopies. It's been used to predict flooding extent from tropical storms and rainfall events by having better models of the surface. Looking at sinkhole formations in places where you have cavities forming in the subsurface and then the land surface subsiding into those. Used it to precisely capture the shape of the Texas coast for both long-term monitoring efforts of how the coast is changing over time, as well as the impact of specific events like hurricanes and the erosion that those caused. And we're limited to how far we can wade into water with hand equipment. The ability to fly over it in a single flight and capture the shape of the seafloor near the beach is just an amazing thing.
When you get advanced equipment like our airborne LiDAR system, which we also have ground-based LiDAR that we fuse together, that leads to partnerships. We partner with the USGS, we partner with DOE, we partner with EPA, we partner with other academic institutions, we partner with industry.
We have done work for the General Land Office, the Texas Department of Transportation, then federal agencies as well, like the Department of Defense, National Engineering Technology Laboratory. The possibilities are really endless.
The Jackson School is bringing together a bunch of different equipment to put on a single platform, an airborne lab, if you will, that's going to let us collect a variety of measurements of the Earth and synthesize those and then address great challenges that we face, whether it be hazards or storms or earthquakes or volcanoes or sinkholes. We're going to be out there. It allows the Bureau to achieve our mission, which is bringing industry, academia, and governments together around challenges so that each of those groups benefits from the results and the information that they need to inform decisions that help the broad public.
Now we are coming to the end of this. Let me give you a quick review. I have some the needed. The students can search more of the new opportunities. So even the sites are there, but there are the names of some important universities which are pioneer in the study of earth science. And then what kind of career you can have in teaching, in the universities, in IITs, stage college, and even some states have introduced geology in even schools. As a geologist, there are different companies in India and throughout the world. As you look, there are some global companies, BHP, De Beers, Petrodyne, and these are some companies and many more. And then you can be a scientist in these pioneer laboratories in India, and there are many new coming up. And here is some link of Earth Science Studies worldwide. It can be circulated to the needy people. And here is the Earth Science Studies in India. There are some important links. And career options. This is the list of career options. You can see time. I have to finish within 2 minutes. So I'm not going to read this out. There are some important links here. Career options. Now you see, at the end, I am ending with these beautiful pictures. This is a geological heritage park. I think it's in Yellowstone Park. You can see these are the beauty of nature. And this is a meteoric lake. A meteor fell in the lake and it is here. And this I took my students to Nathula, Sikkim, when I was in Mizoram University. So this is the end.
Thank you so much, sir. I must say that your presentation, your slides, and the photos which you have used to explain us this concept was awesome. I mean, we haven't seen such type of beauty in our slides. So it's an honor to be, see all those things. So all the dignitaries, as we all draw our webinar to a close, I would like to take a moment to express our heartfelt gratitude to our distinguished speaker, Professor Rahul Verma. Thank you, sir, for delivering such an insightful and engaging presentation on technological advancement and opportunities in earth science. Your in-depth exploration of all the geography and the earth, your science, all these things has provided us with a profound understanding of how these innovations are shaping the future of earth science. Your expertise and ability to convey complex concepts with clarity and enthusiasm are truly commendable, sir. It's clear that your work is at the forefront of this field, and we have all benefited greatly from your knowledge and perspective. So, we understand the efforts and presentation that goes into such a presentation. It requires a lot of hard work, and we sincerely appreciate the time you took to share your knowledge with us today. So on behalf of Mangalayatan University, Jabalpur, I thank you once again. We are grateful for your contribution and look forward for our future opportunities to learn from you. To our attendee, thank you for your participation and engagement. We hope you found the session as valuable and inspiring as we did. Have a wonderful day, and we look forward to seeing you in our next event.
Yeah,
Thank you.
Thank you, ma'am. Actually, I am also thankful to Professor Rao. He suggested me this topic, and I also enjoyed preparing this presentation, and even I learned a lot of things. So I am still learning, and I am also growing. Thank you.
So thank you so much. Thank you all the participants, sir. We will meet you soon, sir.
Thank you. Thank you.